Inductive reasoning is looking at examples to arrive at a conclusion, or looking at patterns, making observations to arrive at a conclusion. And that's what Sherlock Holmes does, right? He makes observations. He looks around him and he observes things and he comes to a conclusion. He's using induction. We're going to go over deduction in section 4. Deduction is using a series of facts to arrive at a conclusion. So the process that Sherlock Holmes comes through, he's making observations, he's looking at things, he's seeing patterns, he's seeing, you know, that somebody has ink on their finger and a pen behind their ear, so he thinks they're a writer. You know what I mean? So he's looking at patterns. So this is okay, kind of a thing that you might induce. If you see somebody every day, and every day they have a travel mug in their hand, you're making the observation that they have a travel mug every day, and you might assume that there's coffee in it, and so you might make the induction that this person really enjoys coffee, just based off the observation that you see them with their cup every day. It's going around. Okay, now the conclusion you might come to is the conjecture. This is a conclusion made using induction. That's a U. Okay, so in my coffee example, you see somebody, they're carrying a travel mug every day, so you induce that they enjoy coffee. Your conjecture is that person really likes coffee. The conclusion. Huh? Yeah. Well, induction is the looking at the patterns to come up with the conclusion. The conjecture is the actual conclusion. Okay, so we're going to use inductive reasoning. We're going to look for patterns. If I want to write a conjecture that describes the pattern, so that's my conclusion based on the pattern I'm observing. I look at the movie times. I have 8:30, 9:45, 11, 12:15, and I notice there's an hour and 15 minutes between each movie showtime. So I might conclude that there's going to continue to be an hour and 15 minutes between each showtime, right? Because if I see that hour 15, hour 15, hour 15, I'm not going to assume, okay, 3 hours till the next movie. I'm going to assume that they're all an hour and 15 minutes because that's the pattern. And so my conjecture is that movies start every hour and 15 minutes. Okay, that would be my conjecture. And then my next item in the sequence, so I'm going to go another hour and 15. So I'm going to be at 1:30 p.m. Each of these is like a dash, so there's 4 here, 4, 5, 6, 7, 8, 9, 10. It's made up of, like I said, it didn't scan well, but this is 2, this is 2, 2, 2. Then my next one, I have my original 10, 11, 12, 13, 14, 15, 16, 17, 18. Then my next one, and my original 18, and then I add, so 19, 20, 21, 22, around till I get to 28, and then 40. So I need to find my pattern. My pattern is basically I'm adding another like piece, right, each time, but each piece is made up of a certain number of dashes. To go from 4 to 10, I added 6. To go from 10 to 18, I add 8. 18 to 28, 28 to 40. Okay, so what's my pattern? Yeah, I'm adding 2 more than the last time each time. Okay. Or you could say, you know, the number you add increases by 2. However you want to word that, just so you recognize that every time you're adding what you added last time plus 2 more. Now, I don't need you to draw this box, but if I were going to create the next box in the sequence, how many would I have to add to it? So I'm going to create a box with 54 dashes. Another numerical pattern. What am I doing each time here? Yeah. So minus 6. So my conjecture is to subtract 6 each time. My next number in the pattern is going to be negative 14. Oh, this one I drew wrong. I forgot to put one of the triangles in it. It should have that. Okay. So we're going to look at this. We have how many triangles here? And here? Right, 1, 2, 3, 4. And here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 1, 4, 16. Yeah. So I'm going to multiply by 4. So my next triangle array would have how many triangles in it? Yeah, 64. And how that would look, put this one back. Okay, we'd have 64, and each of these would then get a triangle inside of it. So if you had to draw it, that's what you do. And that's how you turn one triangle into 4, is by putting an upside down triangle in it. And so that's how it ends up being multiplied by 4. So if we look at, we have this woman owns a hair salon and she's collecting data on the number of customers for the weekends, basically Friday, Saturday, and Sunday for 6 months, because she's trying to decide if she should increase the number of stylists working on the weekends. So she needs more people working on the weekends. Here's all of her data. Do I need to look at Friday, Saturday, and Sunday, or can I just look at the totals? The totals, right? And I'm going up, I'm going up, I'm going up, I'm going up, and I'm going up. So she's going up every month in the number of people that come in on the weekend. So the conjecture, well, sorry, not the conjecture, the pattern is that the number of customers is increasing. Our conjecture is what? She wants to know if she should increase the number of stylists. What do you think? So the conjecture is she should increase the number of people. If we look at a counterexample, any one example that proves a conjecture false. Okay. If we look at our coffee person, we had, like somebody's bringing a coffee mug to school every day, like a travel mug, and you make the conjecture that they drink coffee every single day at school. If 2 weeks ago on Tuesday they had tea, that makes your conjecture wrong. We only need one example that's not true for the whole statement to be false. So if we look at this one, if n is a real number, then n squared is greater than n. Okay, and you might think that might be true, because if I say, okay, well, 3 squared is 9, and 9 is greater than 3. Right. If it's 1, they're equal, not greater than. So n equals 1 is a counterexample. So is 0, and so is any fraction. But you don't have to list every counterexample. You just list one. You find one thing that makes it false, and the whole thing is false, and you're done. If we look at, if jk equals kl, then k is the midpoint of jl. Well, can you think of an example where j, k, and kl might be equal length, but k isn't the midpoint? What if I have a triangle and it's isosceles? And jk and kl are the same length, but k is not the midpoint. Or any other polygon with two sides, jk and kl, the same length. Or an angle. Basically, if you can draw any picture that's not a straight line with k at the midpoint, I could just take and make a bend, right? And make that j and k and l, and if I say those two are the same length, k is not the midpoint because it's not a straight line. Straight line segment, sorry. So if you can think of any picture at all, you can put that in there as the counterexample. If n is a real number, then negative n is negative. How if n equals 0? If n equals 0, what's negative n? 0. Because there's no such thing as negative 0, right? Or what if n equals negative 3? Then negative n would be positive 3. So just anything like that you can find that proves it false. Okay, and finally, if A, B, and C is congruent to D, B, E, then A, B, C, and D, B, E are vertical. Maybe. Unless it's like that. Or any other two angles sharing a vertex B that aren't vertical. So see if you can make any kind of conclusion at all that you can make from the information you've given. Okay, so draw a picture, look at things, and figure out what conclusions can you draw from that. Okay, so when I looked at number 5, I drew A, B, and C collinear, and then D was between B and C, but it didn't tell me how far between. So I can't make any midpoint or length kind of decisions. All I can tell from the picture I drew is that they're all collinear now. So A, B, C, and D are all collinear. Point P is the midpoint of NQ. That tells me that these lengths are the same. So I can say NP is equal to PQ, or, sorry, I forgot to put the segment. The segment NP is congruent to the segment PQ. Okay, when I have 1, 2, 3, and 4 form 4 linear pairs, the only way this can work is by having an X. So I have my linear pairs. I have 1, 2, 2, 3, 3, 4, and 1, 4. So I could say that angles 1 and 3 are vertical, angles 2 and 4 are vertical. Maybe you drew it the other way and you end up with like 1, 2, 3, 4 or something. You could have the numbers a little different. Angle 1 is congruent to angle 3, angle 2 is congruent to angle 4. I could say that I have 4 sets of supplementary angles. These would all be valid conjectures. You wouldn't have to list all of them though. And then knowing that angle 3 is congruent to angle 4 doesn't really tell me much of anything other than that their measures are equal. Because I don't have enough information to really draw like a picture and know what it is. So for these next 4, if it's true, just say true. If you can think of anything that would make it false, you've got to say it's false and come up with a counterexample. So why don't you try those? Okay, number 9 is false because I can have any 2 angles form a linear pair. One could be 5 degrees and the other one could be 175, or anything like 1 and 179, anything in between. So if I said this was, say, 30, then this would be 150. They are a linear pair, but they're not congruent. If AB, BC, and AC are congruent, well, the only way you can get an AB, BC, and AC is if you make a triangle, because that's the only way it connects up correctly. And if they're all congruent, you have an equilateral triangle that they're not collinear. If AB plus BC equals AC, then AB equals BC. No. AB can be 10, BC can be 5, and they'd equal 15, or any other numbers that you put in here. So I could pick any number. The only thing that would make these two congruent is if B was identified as a midpoint. And then finally I have angle 1 is complementary to angle 2. That means 1 plus 2 is 90. Angle 1 is complementary to angle 3. That means 1 plus 3 is 90. So 2 and 3 would have to be the same because 1 is the same as itself. Does that make sense? So this one would be true. Any questions on these? Well, see how I have AB, BC, and AC? So when I try to look at that, okay, if I draw AB, and then if I draw, well, let's say I try to make it collinear. I go AB, and then I do BC, and then I say AC. Well, if this is AC, it's not going to be congruent to these two because it's those together. Does that make sense? So the only way I can make this to where I have an AB, a BC, and an AC that are all the same length is if it curves around like this, and these are all 3 the same. Does that make sense at all? Okay. Logic is a series of statements generally leading to some sort of a conclusion if you talk about formal logic. But they're statements. They're sentences that are true or false. There are no questions. It's a sentence, and it's either true or it's false. There's no gray area with logic. Usually they're represented by the letters P, Q most commonly, and then sometimes we add R if there needs to be a third sentence. The truth value is whether or not it's true or false. So if the statement P is a rectangle is a quadrilateral, that's true because a rectangle has 4 sides. So the truth value of that statement is true. If I had some other statement Q that said squares are round, well, that statement would be false. Okay. Now, negation is when you take the opposite meaning. And the symbol is a tilde and then the letter. And it's read as not P. So we have P and then we have not P. And so in this example, not P would be a rectangle is not a quadrilateral. That would be false. And not Q would be that squares are not round. This would be true. So P and not P have opposite truth values. Q and not Q have opposite truth values, but the not can sometimes be true, just like the regular one can sometimes be false. So just because it has a not in front of it doesn't make it automatically false. Because in this case, squares are not round is true. Because squares are round was false. A compound statement is just the same as a compound sentence would be in English. So these are two statements joined by the word and or. Okay, so just like a compound sentence, but we don't have all the other joiners, just and or, not but, nor, none of those, just and or. So conjunctions are joined with the word and. And it's a conjunction because it's adding together. Have you guys ever heard of like conjoined twins? Co means together. So conjunction is like putting the two sentences together with the word and. And so if we had, let's say P is that a rectangle is a quadrilateral. Lateral. And let's say we had Q, a rectangle is convex. Okay, and these are both true. I could have the statement a rectangle is a quadrilateral and is convex. Okay, now the symbol for and is an upside down V. So this is the symbol. So we could say this sentence is P and Q. That's how we would read that, P and Q. This is true, and that is true, so that makes the whole thing true. Two true statements put together give you a true statement. When we look at the truth value of conjunctions, I've got three statements. The figure is a triangle, the figure has two congruent sides, the figure has three acute angles. Okay. Let's just look at these for right now and say whether these are true or not. Okay, the figure is a triangle. Here's our figure. Would you agree that's true? The figure has two congruent sides? True. The figure has three acute angles? False, because it's a right triangle, right? So I have two true statements and a false statement. Okay, P and R, that's true and true. They're both true, so the overall statement is, sorry, yes, I'm looking at not R below me. I was looking at the thing, okay. P and R, yes, okay. True and false. Okay, if one is true and the other is false, the whole thing is false. Okay, Q and not R, well, Q is true. If R was false, not R is true. So I have true and true, so the whole thing is true. Okay. If I have P and Q, I have true and true, so the whole thing is true. Not P would be false, because P was true, so the opposite is false. And not R is true, so I have false and true. That makes the whole thing false. So if you have the word and, they both have to be true in order for the compound sentence to be true. Okay. That's like, if the first part of your sentence is I'm going to jump in the water, and the second part of your sentence is I'm going to stay dry. I'm going to jump in the water and stay dry. No, you're not. You can either jump in the water or you can be dry, right? They can't both be true. I can't jump in the water and be dry. So kind of think of it that way. And means they both have to be true or the whole thing's not true. So when we look at this, you want to decide which of these are true first. Then you look at your truth values. So why don't you go ahead, there's 6 of those. So why don't you go ahead and do the 6 of them, and then we'll come back to it in just a second. I forgot to do the disjunction first. Okay, so disjunctions use the word or. Sorry, that's red. Okay, and the symbol is the upside down V. And so if I have P, or sorry, not an upside down V, a regular V, if I have this is saying P or Q. Okay. And when we look at disjunctions, January is a fall month. That's false, right? Because January is winter. January is winter, so that's false. January has 30 days. False. January 1st is the first day of a new year. True. Okay. Q or R. This is true, false, or true. When you have or, you can have one false as long as the other one's true, false or true, and it's still true. Okay, so with or, Okay, so as long as we have one true, then the whole thing is true on an or. You have to have both of them to be false for the or statements to be false. So if we look at P or Q, this is false or false, so the whole thing is false. Not P is true, and then true, true or true will give me true. And then R is true, P is false, true and false, sorry, true or false gives me true. So the only way that you get an or that's false is if both statements are false. If this one was true and that one was false, yeah, it doesn't matter. As long as one of them's true, it's still true with an or. So with a false, the only way they're true is if they're both true. And with an or, the only way if they're false is if they're both, sorry, with an and. With an and, they have to both be true to be true. With an or, they have to both be false in order to be false. Does that make sense? Yeah, a V is the symbol for or, and then an upside down V is the symbol for and. Sorry about that. So now we'll go through and we'll try these now that you've seen the ors. One of the tools that you can use to determine whether a logic, like a statement, is true or false, or how many options there are for it to be true or false, is to use a truth table. This organizes truth values. Okay, when we make a truth table, okay, the simplest one is negation. So I have P and I have not P. Okay, if P is true, not P is false. If P is false, not P is true. The next one we have would be a conjunction. So I'd have P, Q, and both, P and Q. I need better lines. Sorry. Just erase this line. Okay. Okay, if P and Q are both true, P and Q is true. True and false is false. False and true is false. And false is false. So you can see the only way you'll get a true with the P and Q is if they're both true. This is just a way to organize our options. With a disjunction, you'd have P, Q, and then P or Q. And here's how this works. We'll go into it in more depth also, but if P is true, Q can also be true. And then P or Q would be true. If P is true, Q could be false. And then P or Q is going to be true. If P is false, Q could be true, which would make this true. Or if P is false, Q could also be false, which would make the whole thing false. So that's how I get the first two columns of true and false. P being true can be paired up with a true Q or a false Q. And then P being false can pair up with a true Q or a false Q. Again. Yeah.
Okay. I'm just looking at the examples. Say it was to say negative P, negative Q, and the false.
We have to change all that.
Okay, but the disjunction.
Uh-huh.
A false and a false, with that two false statements, if you made it a negative Q, would that make that statement true?
Yes.
Instead of false.
Yes, because
Right.
we've already, because you'd make them opposite, which would make it true. Now we're going to construct one. We need to construct a truth table for not P or Q. Okay, so I need P, because I have to have P in order to have a not P, and I need a Q. And then I need my not P, and then I need not P or Q. Okay, if P is true, and then Q could be true, but if P was true, not P is going to be false. So I'm doing false or true, that's true. But what if P was true and Q was false? Because this I did true, true, but I could do true P and false Q, which would still give me a false not P, and then I'd have false or false. So that would be false. And then I say, well, okay, but what if P was false to begin with? Q could be true, and then not P would be true, and then I'd have true or true, which is true. But what if both P and Q were false? Well, not P would be true, so I'd have false or true, which would be true. Let's just say I'm only doing P and Q. That's two letters, so I do true, true, false, false, and then I do true, false, true, false. And that gives me all of my combinations. So true, true, false, false, true, false, true, false. If I ended up with, like, say, 3 letters, I have 3 possible combinations now. So I do true, true, true. I think it's just 3. Oh, no, it's more than that. Yeah, hold on. So I could have true, true, true. I can have true, false, true. I could have true, true, false. I could have true, false, true. I could have true, true. Did I do true, false, true? I did. I did true, false, true twice. Ah, stop. Hold on, I don't know what I just did. Okay, hold on. I normally plan these out ahead of time before I just randomly say, hey, let me show you this. Okay. So I have P, I have Q, and I have R. So if P is true and Q is true and R is true, what if P was Q and Q was true and R was false? So I have true, 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 false. Or I could have true, false, true. Or I could have true, false, false. So 4 trues. And then I need 4 falses. Because I could have false, true, true, and false, true, false, and false, false, true, and false, false, false. So however many letters I have to have 2 for each additional letter. So P and Q, I have to have 2 trues, 2 falses for that extra Q. PQR, I have to have 2 for the Q, 2 for the R. 2 for the Q, 2 for the R. Okay. So we're going to construct a truth table for not P and not Q. So I need a P, and I need a Q, and I need a not P, and I need a not Q, and then I need a not P and not Q. So you always have to have the P and the Q. That's your basic. And then if you have the knots, you have to throw in 1 column for each of the knots, and then you have a column for the conjunction. Okay, so I have true, true, false, false. And this one I do true, false, true, false. If P was true, not P is false. And when P was false, not P is true. So it just flips those. And then if Q is true, it's now false, true, false, true. And then not P and not Q. I have a false and a false. That's false. I have a false and a true, true and false, or true and true. Yeah. So try to work on just completing these two real quick. There's only like a minute left though, so if we don't have time, I'm going to go ahead and write the homework on here.